when we are doing these heating curves, you should be able to look at these without having these words in blue written in and know exactly which phase you're at or which transition you're going through. Okay? So what I want you to see from this is the following. When you have a solid, that's right here. So this is going to be a solid. When you are transitioning between that solid and the liquid phase, during that transition, what is happening to the temperature? During the transition from a solid to a liquid, what happens to your temperature? It stays the same. During a phase change, the temperature stays the same. That is important. During a phase change, the temperature stays the same. So you could easily identify where those phase changes are occurring because the temperature is not changing. During a phase change, the temperature does not change. That is an important point. That is why I'm repeating it 3, 4, 5 times. If you're having trouble sleeping tonight, pull this video up, listen to it again, and listen to me say it another time. During a phase change, the temperature doesn't change. Now, why? Why is that? Okay, that's what I want to talk to you about. What have we been studying? What is the topic of this unit? IMFs, okay? What is happening during this phase change is if we are adding heat energy in, heat added, see? If we're adding heat energy in, those IMFs are being reduced. And all of that energy, all of that focus of that energy is going on reducing those IMFs. So there's no energy left over to be able to increase the temperature. Once that material has transitioned then, has gone through that process, those IMFs have been weakened in the case of going from a solid to a liquid. Then that energy can kind of turn its focus back around to increasing the temperature. But until those IMFs are weakened enough, that can't happen. Okay? So in this process, all of the heat energy is going to reduce the IMFs if we are adding heat in. Okay? At this point, we have a liquid. Okay? Temperature is increasing, temperature is increasing, temperature is increasing. Here, we're going through vaporization. So we're changing from a liquid to a gas. So here we're getting rid of those IMFs. They're not going to have the intermolecular forces to keep those molecules close enough together anymore. So they're going to pull them apart, and when they're pulled apart and there's no IMFs present between them, then they're going to be in a gas state. And then after all of those IMFs have been taken away, then the temperature can increase again. But all of the energy here is going into getting rid of those IMFs. Here, it's reducing them. There's still going to be intermolecular forces at play, okay, because it's a liquid. Here, it's getting rid of them completely. Does that make sense? No IMFs present. We're in a gas state. Okay. Now, how can we get that gas state back into this? Well, we can cool it down and go the opposite direction. So here we're reforming. If we go back the other direction, we're going to reform the IMFs. And here we're going to strengthen them even more to get back to a solid. That makes sense? Okay. So if you were to see this without the blue lettering here, and we were saying that we were adding heat in, you would be able to say, okay, this is a solid, this is a liquid, this is a gas, this is where it's melting because we're adding heat energy in, and this is where we're vaporizing. Okay. Now, if you remember back to, I want to go chapter 3 again. If you remember back to chapter 3, there are 2 forms of vaporization. Okay, there's a slow form, which is called what? You get some water on your hand, you let it sit there.
Oh, evaporation.
Evaporation. And then there's a very rapid one, which is called, I want some mac and cheese. What do I do?
Put it in the microwave.
Boil it. I boil water on the stovetop. Okay, so boiling. So vaporization, I have boiling, or I have evaporation. Evaporation is very slow. It occurs at the surface of the liquid. And boiling is very rapid. You get those bubbles forming at the bottom. They're less dense. They rise up. They break through the surface. Okay. All right. Intermolecular forces are between molecules. They explain properties such as boiling and melting, surface tension, capillary action, vapor pressure, miscibility, but they don't have much effect on gases because they are moving around too quickly. Did we talk about, I don't think we talked about vapor pressure, and we didn't talk about miscibility. We need to talk about those. We didn't talk about capillary action either. Did we? I need to talk about that. We talked about surface tension. We talked about melting and boiling point. An increase in IMFs means an increase in these. Okay, I need to copy this. I need to take this into a Word document where I can actually write on it, because gosh knows we wouldn't want anything to work well around here for me. Okay, so Control V, and then I can talk about these things. Okay, so surface tension we talked about. Capillary action is where a liquid moves up a thin tube due to the attraction between the tube and the liquid, called adhesion. You can also see that like with a paper towel. Okay, let me see if I can find my little video here too. YouTube blood of a capillary tube. There's this guy. This is the one that I usually use here.
Now we're going to use the cow blood. Hanging drop of blood.
You don't need to listen to this person though. Okay, so this is cow blood, so you don't have to like faint on me or anything. Okay, so, but this is called a capillary tube here. So this is, just pretend that this is like red water, so you don't faint on me. Okay, but what I want you to see is the capillary action. There's this tube is just like a straw essentially. Okay, and what happens is when they put that water droplet on there, watch what happens to it. They're not sucking it, they're not doing anything. It just gets drawn up that tube. There's no pressure, nothing. It just pulled right up there. And that's because of the adhesive forces, the adhesion, the intermolecular forces between the glass in the tube and the liquid. So there's intermolecular forces that are attracted to one another, and it moves right up that tube. Okay, Don't faint on me. I used to teach forensic science, and I've actually had a couple kids faint on me when we talked about blood. So, all right. Vapor pressure. This is one of the things that I needed to be able to draw for. So that's why I brought us over into the world of Microsoft Word. All right. So vapor pressure. If we have something like water, for example, okay, and vapor pressure has to do with a capped, it has to have a capped off container, okay, because otherwise you wouldn't have pressure buildup. It would just go out into the room, okay. So if we have something like water here that has high IMFs, so this is water, it has IMFs compared to, we talked about acetone a few weeks ago. Remember that? I gave you an acetone explanation. So here we've got the same kind of container at the same amount. This is acetone. Acetone has lower IMFs compared to water, at least. Okay. So when we have these in here, since this has higher IMFs, what's happening is, I'll let you draw that because you're not going to be able to listen. I have to slow myself down sometimes. Get so excited about this stuff. IMFs is one of my favorite chapters of the year. I really enjoy it. So, all right. So anytime we have a liquid, there's constantly kind of an exchange between the liquid form and the gas form. Some of the liquid molecules are going up into the gas stage, and some of the gas are going down into here. Okay, does that make sense? They're just constant. That's if this is a capped thing. If it's not capped, then it'll go into a gas and it goes off into the atmosphere and you can't keep it. So that's why we have to talk about vapor pressure in a sealed container, okay, like a water bottle. Now, acetone, because it has fewer IMFs, we get more of it going up into the gas stage compared to the water. You know, it's going to have constant exchange, but you're still going to have more in the gas state up here than you would have for the water, okay? And when that happens, that causes pressure on the container. This gas is called a vapor, and so they call that vapor pressure. So lower IMF equals increase in vapor pressure. That makes sense? Why? Okay. And then lastly, we talk about something called miscibility. Anybody have any idea what miscibility means? Just throw it out there. Nope. Anybody else? Mixing. Will something mix with something else? Okay, so this means mixing. Will it mix? Will it mix together? Okay, so that's what we're asking. So when your teachers talk to you back in elementary school and they talk to you about oil and water, what do you know about oil and water in relation to this? They don't mix, okay? What did your lovely elementary teachers, doing the best that they can do, what did they tell you as for the reason why oil and water do not mix? Density. Exactly. That's what they told you. Okay? It was wrong. Okay? Now, density, what they did have right was the fact that the oil is going to be on top of the water. We'll give them that. Okay, the oil is less dense than the water, and that's why it's going to float. Okay, but the reason why they don't mix has to do with IMFs. Okay, and my guess is they don't even know what an IMF is, and that's okay because they haven't had that ability to understand it. And I'm sure that there's stuff that I'm teaching you at this level that I've gotten wrong. Okay, so you get into upper level college chemistry, and they'll probably go, well, those high school teachers, when they told you blah, 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 they were wrong. And that's okay. You know, it's just the level of education that we've had. I can only do so much. I will also tell you that I've told you certain things this year that I'm going to back up and remove. And I've kind of lied to you a little bit this year. So if you take AP, I've already done some of that. Okay. And I'll come clean with you. But you're not at the, I don't want to try to, I try to simplify stuff for you so that you can understand it now. But then but next year I'll be able to add more stuff in, and you'll be able to go, oh, okay, yeah, you lied to me, Libby. And I'll go, yeah, I did. But you'll understand why once I explain it, okay? But theirs is because they didn't quite understand it, okay? And that's okay. Like I said, I'm sure that there's stuff that I'm doing wrong too. But it's it's the best we can do. Now, why is this? Well, oil is nonpolar and water is polar. Okay? And you might be able to real quickly leap and be able to get that, but let me explain it a little bit better than just in those terms. Okay? When I have water here, remember that water is polar, so it has a negative end here and a positive end down here. Okay? When it's by another water molecule, it's going to get attracted with those IMFs to the other water molecule. The positive and the negative here. Okay? So I'm just going to represent this with a W now because I need to be able to get more kind of drawn in here. Okay? So I've got my water molecules, and they're going to be attracted to another water molecule and another water molecule and another water molecule and another water molecule because of the positives and negatives. Oil is nonpolar. So oil comes along, it doesn't have a positive or a negative end. It's not going to be able to get into this network because it's not going to get attracted to these other water molecules. Because remember, they've set up this little web where they're like, hey, I like you, and they're all kind of holding hands. They're not going to let this oil in because oil doesn't have a charge. It doesn't have a hand to reach out and go, oh, here we go. You know, I've got a positive and a negative end. Okay? The water is going to exclude it. The oil will sit on top because of the density. Okay? But the water is going to all stick together because of those IMFs. So it has to do with IMFs as far as whether they mix or not because of density. Okay? Does that make sense? We'll see if I get through these notes today. Again, I like IMFs. Okay, so we talked about inter and intra. We've already talked about that. Do you have anything on your sheet to have to write about that? Okay, I didn't think so. We talked about all that. Melting and boiling point, higher the intermolecular forces, the harder it is for it to melt or boil. We talked about that. Surface tension, we talked about that. And you'll actually see, like, mercury has really stupid high IMFs. So you know how, well, it won't let me draw. Maybe if I go, maybe it will. If I go like this. Maybe it will. Oh, yeah, here we go. No. Piece of poo. Oh, there we go. Now it's letting me. So you know how when you have water in a graduated cylinder and you're reading that, you know how it goes like this? If you had mercury, which we can't have anymore, it's dangerous. Mercury's IMFs are so much greater than water's that it actually forms a meniscus that's like this. It's crazy. And that's because of those super high IMFs. And if you lay these out like on a counter, you can see kind of the surface tension here too. That's why it forms, water has like a skin that it forms too. We talked about all of this. Did you write any of this stuff down that I was going through? Vapor pressure. I guess I did have that stuff written in here. Okay, I'll let you, I don't know if you want to write any of that down. Do we have time? We have time. Yeah, we got plenty of time. Full screen. Journey, like the band? Wait, that's retro. That's back when I was in middle school. Holy cow.
Yeah. My stepdad, I think he's had it that long.
I don't know. I kind of, guys didn't wear pink back then.
It's at least like 50 years old.
It may be, but yeah, I don't know that it's back from the 80s. That'd be really dated. All right, good? Good. Yeah, things have changed a lot, y'all. For the good, for the better. Everything's good. Okay, vapor pressure, we talked about that. Do you need to write any of this down, or did you get it from my discussion? Good? Okay, I'll keep moving. And then phase changes. We talked about these back in chapter 3. You should know what these are. But in case you missed it, or you don't know what these are, the ones that people struggle with typically are gas to a solid, which is deposition or deposition, and a solid to a gas, which is sublimation. So if you don't remember those. And then again, vaporization, remember we have 2 examples of that. We have a slow version, which is evaporation, and we have a fast one, which is boiling. Good? No? Okay. Let's see here. What else I got? Phase change. Oh, endothermic versus exothermic. So endothermic means that we're adding heat in. Exothermic is we're removing it. I always think of this as exiting. So the heat is exiting the system. I'm trying to write with my mouse. It's not going well. So if I go back over here, if I'm going this direction, come on, write for me, thank you. If I'm going this direction from a solid to the gas, or if I'm going solid liquid to gas, this is endothermic. And if I go back the other direction, this would be exothermic. And essentially, like what a refrigerator is doing is it's removing heat energy from your food, drink, whatever that's in there, from your material that you put in the fridge. It's removing that heat energy. And that's why the motor runs, okay? It's removing that heat energy out to the outside. It also cools in there, but the cooling process is by removing heat energy. So that heat energy is exiting the system. Here, this is endothermic. So you put something on the stovetop and heat is entering into that system. You're adding heat energy in. And you can kind of see solid, liquid, gas, right? You could start out with ice in a pot and take longer, but you could do it. All right, and then these are just going, like, you guys know what these are, so I don't really need to go through. That's just talking about what those different things are. All right, phase diagram. There's one more thing that we need to cover, which is a phase diagram. You don't need to write down this here. And I don't know why this pink line is here, so don't put that in. Write in green, write in aqua, write in red, and then you can do the rest of this graph. So we have different sections of this graph, which I was trying to. I have the highlighter selected. You see it? This thing just hates me. Well, I was going to try to highlight this section here. This section here would all be solid. Okay. The section down here and all up here would all be a gas. And that's why they put vapor here. Okay. And this section they have labeled as a liquid. Now, this is the sublimation line, which means that if we go from a gas to a solid or back and forth, if we go from a solid to a gas, we would go through sublimation. Does that make sense? This is the ice line. If we go from a liquid to a solid, then that's going to form into ice. And then here, if we go from a liquid to a gas, that's why they call this the steam line. Okay? Now, this point right here, where all three phases can exist at the same time, that is known as the triple point. So the point here where all three phases can exist at the same time is the triple point. Let me see if I can find a YouTube video on that. I used to have one that I would show. It's kind of cool. Well, this one looks like it's got, I don't know why the water is colored, but I'm going to show it here. So, that guy. He's going to talk a lot here. Let's see if we can actually get to the, so he's going to tell you about water. He looks like he could put you guys to sleep at night too. So he's got this set up so that he's got solid water, he's got liquid in here, and then he's got gas, and it's all happening. And he has it in a contained environment here because he has to increase the pressure. Okay, normal atmospheric pressure is how many kilopascals? 1 atm. Okay, so that's really low. Okay, so he has, what was that like? What did he have for the kilopascals there? 1.19 kilopascals. Yeah, he's got the pressure way down. Okay.
Ground force can form on solid surfaces by the
yeah, so this is showing you frost. Okay, that's deposition. So that's where you go from a gas right to a solid at the same time. So here's your solid forming. He's got gas in here, and he has so solid, liquid, and then the gas is forming. But he has to do that under, he has to reduce the pressure. So that's why this is all set up all fancy here. Okay. Oh, I bet those are just glass beads in there. They do that sometimes. So here we go. So it's starting to boil. Do you see how it was boiling there? It was bubbling, and then it's got a solid forming, and it's got the liquid in there still at the same time. It's kind of cool. So there's some bubbles coming up. There's the bubbles. It's boiling here. It's freezing, and it's a liquid at the same time. There's another couple videos here. I think this might be the one that I've shown in the past, actually. Here, they're going to get it boiling here. Starting to kind of get little bubbles down here. See down there, the bubbles are forming. They're coming up. And you've got a solid here at the same time, and then the liquid. But they have to change the pressure, so that's why they have it in one of these special vacuum pumps is what they're called. And I actually have a vacuum pump in there. I don't have any heating element to be able to do this part of it, or cooling element or whatever they're doing. But But I actually can boil water at room temperature for you guys, and I'll do that in our next chapter. See, you want the next chapter, Ernesto. It's a good thing. All right, so that's called the triple point, and that is the end of chapter 12. So you have for me, let me go over to your classroom here. I will be posting this shortly. I need to get the video uploaded, and then you're going to have this 12-4 worksheet that you're going to be working on, and I'll get that posted for you in just a couple minutes. So if you can hang tight, I do have some work that